Welcome to aminacademy.com. In engineering thermodynamics, let us discuss about system, equilibrium, process, and functions, etc. A system is in thermodynamic equilibrium if the temperature and pressure of all points are same. There should be no velocity gradient. The chemical equilibrium is also necessary. Systems under temperature and pressure equilibrium but not under chemical equilibrium are sometimes said to be metastable equilibrium condition. It is only under thermodynamic equilibrium conditions that the properties of system can be fixed. Thermodynamic equilibrium leads to the large scale definition of temperature. When two objects are in thermal equilibrium, they are said to have the same temperature. During the process of reaching thermal equilibrium, heat, which is a form of energy, is transferred between the objects. Look at here hotter body, here cold body, heat flow from hotter to cold body until the equilibrium state reach. In that phase, thermal equilibrium, the temperature of the system does not change. In thermal equilibrium, temperature does not change. Mechanical equilibrium, there are no unbalanced forces. There are no unbalanced force. That means while equilibrium reach, there are only balanced forces there. Chemical equilibrium, after reaching chemical equilibrium, no chemical reaction takes place. No chemical reaction. Now we will discuss about thermodynamic properties. A property of a system is a characteristic of the system which depends upon its state but not upon how the state is reached. Here, thermodynamic properties are defined as characteristics feature of a system capable of specifying the system state. The thermodynamic properties of a material are classified in several different ways: measured properties, fundamental properties, derived properties. Properties of the system directly accessible in the laboratory are known as measured properties. For example, volume, temperature, and pressure. Next, the properties of the system directly related to the fundamental law of thermodynamics are known as fundamental properties. For example, internal energy and entropy. Next, the properties of the system that have specific relation and include combination of measured and derived properties are known as derived properties. Example, enthalpy gives free energy. The fundamental properties are and derived properties cannot be measured. The thermodynamic properties of the system are divided into two general classes: extensive property and intensive property. An extensive property's value depends on the quantity or a size of matter in the system. In contrast, extensive variables help characterize the specific system being analyzed. For example, mass, volume, internal energy, enthalpy, heat capacity, entropy, Gibbs free energy. Those properties do not depend on the quantity or size of matters are known as intensive properties. Intensive property may vary from place to place within the system at any moment. For example, density, pressure, temperature, specific volume, specific entropy, thermal conductivity, thermal expansion, compressibility, and many more. These are intensive properties. Next, we will explain thermodynamic state. State is the condition of the system at an instant of time as described or measured by its properties, or each unique conditions of a system is called state. It follows the definition of state that each property has a single value at each time. The thermodynamic state is a set of variables of a thermodynamic system that must be specified in order to reproduce the system. That means in thermodynamic state, it can reproduce the system again. The individual parameters are known as state variables, state parameters, or thermodynamic variables. Now, some thermodynamic states variables are: to define the state of system in the thermodynamics, we use various parameters. These parameters are called state variables. It includes temperature T, pressure P, volume V, entropy S, enthalpy H, internal energy Q, mass M, density rho. It must be noted that the state variables do not depend on the path taken to reach that state. It is independent of path to reach the state. Intensive and extensive variables. Extensive variables are state variables that exhibit the size of a system. For example, volume is an extensive variable because it helps determine its size. Intensive proper variables are the state variables that do not provide any information about the size of the system but indicate different details on the system. Examples of intensive variables are pressure, temperature, etc. A thermodynamic process is a process in which the thermodynamic state of a system is changed. Means state change, that is called process happening. A change in system is defined by passage from an initial to final state of thermodynamic equilibrium. Further, thermodynamic process we'll discuss. A process occurs when the system undergoes a change in a state or an energy transfer at a steady state. A process may be non-flow, in which a fixed mass within the defined boundary is undergoing a change of state. For example, a substance which is being heated in a closed cylinder undergoes a non-flow process because it cannot flow, the energy cannot flow outside, heat cannot flow outside if it is conditioned. Closed system undergoes non-flow process. A process may be flow process in which mass is entering and leaving through the boundary of an open system. In open system, that mass can enter leave from the boundary of an open system. Thermodynamic process is a process in which the thermodynamic state of system is changed. Change in a system is defined as a passage from an initial to final state of thermodynamic equilibrium. Now, process can be classified as: in thermodynamics, a quasi-static process is referred to as a slow process. Second one, it is a process that happens at an infinitesimally slow rate. There are conditions of flow. Quasi-static process is first is slow process, second one is infinitesimally slow rate. A quasi-static process has all of its state in equilibrium. Quasi-static process is one in which the system is in the thermodynamic equilibrium with its surroundings at all times. Example of quasi-static process, and that is not idealizable as reversible is slow heat transfer between two bodies on two finitely different temperatures, where the heat transfer rate is controlled by a poorly conductive partitions between two bodies. Quasi-static process means almost slow. A quasi-static process is also called a reversible process. This process is a succession of equilibrium states and infinite slowness is its characteristic feature. Next, we'll discuss thermodynamic cycle. Here, before that, and example of quasi-static process is that is not idealizable as reversible is slow heat transfer between two bodies on two finitely different temperatures. Next one, thermodynamic cycle. Any process or series of processes whose end states are identical is termed as cycle. The process through which the system has passed can be shown on a state diagram, but a complete section of the path requires in addition a statement of heat and work crossing the boundary of the system. Thermodynamic cycle consists of linked sequence of thermodynamic process that involves transfer of heat and work into and out of the system, while varying a pressure, temperature and other state variables within the system, and that eventually returns the system to its initial states. About thermodynamic states, we'll discuss in future videos detail. Look at here, heat, boiler, that means what? That means boiler supplies heat to the turbine and work is done by the turbine and excess heat come to heat condenser and heat something out through the condenser. The condenser gives to the water, heat reduced water, and to the pump, and the pump supplies pressurized water to the boiler and water heat up in the boiler, and the cycle is continuing. This is a continuous process and repeated process. It's called a thermodynamic cycle. Next, point function. A function, also known as a state function, is a function whose value depends on the final and initial state of that thermodynamic process, that is irrespective of the path followed by the process. Example of point functions are density, enthalpy, internal energy and entropy. Yeah. Or look at here, for point function, integral 1 to 2 dV, change in volume, integral of change in volume equal V2 minus V1. Here, this is for example of point function. Next is path function. There are certain quantities which cannot be located on a graph by a point but are given by the area or so on that graph. In that case, the area on the graph pertaining to the particular process is a function of the path of a process. Such quantities are called path functions. For example, heat, work, etc. Now, heat and work are inexact differentials. Their change cannot be written as a differential between their and states. Therefore, we can discuss about further. The path function is a thermodynamic property that depends on the path between the initial and final state is known as the path function. The path functions depends on the path taken or covered between two initial and final states. For example, work and heat. Here, path 1 to 2 maybe it reach path 1 to 2, or they said through a path A 1 to 2 it can reach, or through path B also it can reach 1 to 2. It is irrespective of the path it takes to reach the final state. Here path function is, look at here, integral dq, change in heat 1 to 2 gives q2 minus q1. Similarly, work done dw 1 to 2, it gives w2 minus w1. So far we discussed the terms regarding thermodynamic state, equilibrium, functions and properties. We have done. Please subscribe our YouTube channel.